Welcome to tonight's panel session on the future of quantum computing. My name is Jill Dobby and I'll be the moderator for the evening. Today we're using Slido, so if you want to pull up a web browser, you can go to slido.com and then you're asked for an event code, and the event code is #Gibbons. With Slido, what you can do is you can post questions, you can like questions and dislike questions. So these questions at the moment are based on the popularity. So I'll also be taking any questions from the audience because you can't all use web browsers in this room. So we'll have a mixture of questions from up there and also questions from the audience. So it's my great pleasure to introduce our panel tonight. The first is Prof. Howard Carmichael from the Department of Physics, and the second is Prof. Chris Calude from the School of Computer Science, both from the University of Auckland. Howard's research is actually in quantum optics, so he has a passing interest, he tells me, in quantum computing. Last night I went and looked up his record. I was very, very impressed with his track record. One thing that's really stood out is that his PhD supervisor was Dan Walls. So Dan Walls was a pioneer in New Zealand who put New Zealand on the map for both photonics and quantum optics, and is very well recognised in New Zealand. Similarly, Chris has a very impressive track record, including being the founding director of the Centre of Discrete Maths and Theoretical Computer Science here at the University of Auckland. And in this role, he organised the first international conference on unconventional models of computation in 1998. And in that conference, there were talks of quantum computing. So that was 21 years ago when people had started talking about it. Okay, so the format for this evening is that I'll get the ball rolling with a couple of questions, and then we'll continue with questions from you. They're not, is the answer to the last question. The last question is why the panellists allowed wine glasses in the room, and they're not allowed wine glasses in the room.
Because this is not the United States.
Until we noticed them, they were neither here nor not here.
Very tricky, very tricky.
We didn't use them yet.
Okay, so Howard, I'd like to kick off with you, and I'd like you to explain a little bit about quantum computing from the perspective of a physicist and what you find fascinating about quantum computing.
Yeah, certainly, I'm happy to do that. First, hello everyone. It's good to see people here, including my wife and even some students. It was said a few minutes ago that I have a passing interest in quantum computing. A more accurate statement is it's impossible to avoid it in my field. The field that within which quantum computing lies is actually, in physics terms, somewhat broader. It has the name quantum information, and it includes certainly first and foremost this objective of building a quantum computer. But there are three other areas which are also very prominent. One is quantum cryptography, which relates to improving security of communications using quantum mechanics. Another one is quantum metrology. The word metrology refers to measuring things. So there the idea is to use quantum mechanics to make more precise measurements. And the last one, which is probably the most widely pursued in physics labs, is quantum simulation. And you can think of quantum simulation as a sort of an analog version of a quantum computer. The basic idea is that you have a complicated physical system on which it's very difficult to conduct controlled measurements, and therefore you take a mathematical model of that system and you transfer it to a controllable quantum device, something quite possibly built out of qubits, etc., so something like a regular quantum computer, but it's specifically designed to emulate that physical system. And because you can control that more fully, access all the knobs in a way, you can answer questions on that controllable device rather than on the complicated actual physical system. Maybe physicists would have different views as to whether doing that was better than actually doing experiments on the physical system in the first place. But let's just say that you have certain advantages in certain cases. What fascinates physicists, or why are they interested in this? And I think I'll say two things. I don't want to take too much time on the first question. One is that these applications, these technologies, simply mesh perfectly with the frontiers of experimental physics in certain fields. Those frontiers can be defined by a push towards the micro world and an increasing need to face up to quantum mechanics and its more subtle and unusual aspects. So attempting to realize these quantum technologies, including a quantum computer, sets a technical challenge for experimenters, and that's what they're all about, is pushing the envelope. So so this is the app of choice. You know, these things they're just perfect to fit with where quantum experimentation had reached. The second reason, and maybe the more apt one for the word fascination, is that quantum computing in particular features the weirdness of quantum mechanics in a very prominent fashion. It works because quantum mechanics has a very, very strange way of describing reality, and no one, including the brightest physicists, really understands how it, well, they understand how it works as a mathematical scheme, but how it relates to reality. And so this is a marvelous playground for physicists to enter into a combined sort of enterprise where you have something in the lab which you can really work with and gives you answers and is doable, and you have in your brain some very unusual concepts about the nature of reality, and you can argue with each other about the philosophical aspects of those two things.
Thank you. So, Chris, would you like to say a little bit about what your interest is in quantum computing and how it started?
Well, it started long ago, motivated by my interests in limits of mathematics and computation. And from my perspective, I think that the fascination of quantum computing is in the possibility of proving mathematically that we cannot build a quantum computer. And if we would have such mathematical results, this will be a limit in quantum physics, a fundamental limit in quantum physics. And this is the most fascinating issue for me.
We could argue about this one.
Sure.
Because it tends to suggest that the mathematics is not simply a way of expressing or representing the physics, it's more fundamental. Whether a quantum computer can be built or not, for me, at a crude level, and we'll come to what being non-crude means in a second, but at a crude level, is a physics question and a technology question. It's just a case of what you can do. If, however, you describe, you define a computing device in a pure mathematical sense, and everything, the essence of it is embodied in certain theorems about what is feasible in principle or not, you may well be able to prove that you can't build a quantum computer. You can't build a physical device that can realize these things. So I think there might be a divergence of directions here. I mean, I think mathematics is simply a language. It's the language of patterns, and science is all about patterns. You see regularities in the way things behave. This is what science is built upon. And mathematics is the perfect language for encapsulating these relationships. But I don't think God is a mathematician. In fact, he's more likely to be a physicist.
Right, but you can have the two going hand in hand.
Oh,
You
yeah,
can have
absolutely. They do go hand in hand.
The theory and, you know, the actual physical
Yeah.
quantum computing. You kind of need both, and, you know, neither is right or wrong.
Yeah, well, I mean, I think the momentum of quantum computing is driven by the thought that you can possibly make the device, because governments really care about that. Big governments care about that, primarily because of Shor's algorithm and the possibility to break codes, factor very large numbers, and make current codes sort of obsolete. If anyone can do that and you're a big government in the world, you want to know about it. And it's a big risk not to assume it can't be done.
Yeah.
But there are two possibilities here, as you said. One is pure theoretical.
Mm.
So I was thinking about a kind of no-go theorem, like, you know, Cohen-Specher theorem, which says that something cannot be done. And the other one is that may not be any theoretical reason not to be able to build quantum computers, but there are, you know, practical engineering obstacles. Mm. So I was interested and continue to be interested in the first aspect.
Yeah, that's more, we're in agreement. We're sort of saying the same thing.
Okay.
That's the problem, though. There's not just two possibilities.
Malcolm's razor.
There's an infinite number of them, surely. It's a superposition.
Oh, well, you're getting at another aspect. I mean, Chris was just talking about two ways of thinking about the whole idea of computation and the possibility to build a device. But you've raised of course, the central question, or the central issue, as about what makes a quantum computer a quantum computer. And I think to illustrate that with an example helps to clarify the very strange nature of the quantum mechanics and the enormous claim that is potentially made by suggesting you can use this nature to solve problems. My example is a string of bits. Take 100 of them, so 100 zeros at once. If you have a string of 100 bits, there are 2 to the power of 100 different ways of organizing them. There are 2 to the power of 100 strings. That's a large number. 2 multiplied by 2 multiplied by 2, 100 times. It's about 10 to the power of 30, so that's 1 followed by 30 zeros. Now, in a regular computer, in a regular conception of a register, you always are faced with 100 objects which are all switched either 0 or 1. And of course, as you compute, then those switches get changed around. According to quantum mechanics, it is possible in principle to set the physical system of 100 qubits up in a physical state that in some sense all 2 to the power of 100 possible arrangements exist at the same time. They are all present in some sense. I want to say always this, you always have to say this in some sense, because it's simply a bizarre suggestion. If you look at the computer and read the register, you will see just one. You'll see a definite arrangement, just one. But while you're computing, you're not allowed to look. Nothing is allowed to read any of these qubits. And the power that enables you to implement algorithms, either faster or algorithms that simply can't be done another way, somehow lies in that enormous space of 2 to the power of 100 configurations potentially being there at every instant. To put it in more concrete, sort of simple arithmetic, mathematical terms, that means in order to store information that tells you what your quantum state is, you need 2 to the power of 100 complex numbers. In a regular register, you need 100 numbers, just one for each qubit. 2 to the power of 100, 10 to the... So there's this enormous mathematical space that plays a role as you manipulate this thing. And without going into details, which I probably couldn't do anyhow, there you see that there's the potential, very likely, to do something more.
Yeah, you look, but what happens when you look again?
When you look again, if you look and then you look immediately again, you see the same thing.
Can I throw a mathematical result here? Okay, thank you. I want to speak about the Holevos bound. So, roughly speaking, no mathematics here. One may able to pack 2 to the n bits into a state, but the number of bits one can reliably get out of this is only n.
Yeah, well, that's the reading bit that I just mentioned. I think that's what you're saying. When you read it, you just get the n numbers.
Yeah, no, but even if you try all sorts of string, you have this huge potential, but at the end of the day, it comes to n.
Yeah, but okay, so
all this 2 to the n collapse.
How are these two aspects interrelated? Quantum mechanics is a statistical theory. It makes only statistical predictions. So if I prepare one of these 100-bit qubit registers in a state which, in some sense, has all 2 to the power of 100 possible arrangements present, each of those arrangements has associated with it a complex number. The sum of the squares of the complex numbers, or the sum of the mod squares of the complex number, adds up to 1. Those mod squares of the complex numbers are probabilities. They give you the probability that if you read that register, you'll get this particular arrangement. So you've got 2 to the power of 100 probabilities. And when you read it, you only get this much out. You read it again, if you prepare exactly the same initial state and you read it again, you'll get a different one out. You'll get a probability distribution of all these different arrangements. Now, the point is that that probability distribution of the results when you read it can depend, or will depend, on the way this state has been manipulated during your computation. So the pattern of outcomes, if you repeat the calculation multiple times and see what you get, the pattern of outcomes can have information which relates to those 2 to the power of n arrangements, and it contains information that has been influenced by all of those many, in some sense, configurations coexisting. This is what is referred to as quantum interference, that different arrangements have an interference with each other. And you get an interference pattern when you produce these probabilities. And what produced that interference pattern is related to your computation. And so that red interference pattern can tell you information that is useful for solving problems. And I have to emphasize, this is all statistical, so you don't just set it up, run it, and it spits out the answer. You have to make repeated samplings of the statistical results, and from their properties, you can extract useful answers.
This explanation brings me back to what you said at the beginning, the gap between what we can do and what we can understand. So you said that quantum mechanics is basically probabilistic and statistics, which I agree, but one has to be very careful here in saying that this is our current knowledge and our current models about this. There is no, ultimate result, as far as I know, which says that there is no better way to understand quantum mechanics except in this way.
There isn't. Yeah, there isn't. There was one very famous person who very much wanted there to be, and that was Albert Einstein. Albert Einstein played a very big role in the early days of quantum mechanics. I mean, if you ever, it's fascinating to read I mean, at the time, this guy was dreaming up relativity, general relativity, winning the Nobel Prize for this and that. He published all sorts of, a large number of papers on the beginnings of quantum mechanics. And over the years, he became disillusioned with quantum mechanics because of these sorts of weirdnesses. And he wanted there to be a more tangible, realistic theory, which nowadays are referred to as hidden variable theories. So that there's something sort of behind the current way that we formulate quantum mechanics, which has additional hidden variables, which will make it tangibly understandable, more objective.
Okay, so we'll move away from how it all works to some of the, practical questions of how it will be used. So one of the questions that's been asked is, do you think the ICT security industry has an inkling of the impact of pragmatic quantum computing?
What do you think?
Chris wants to know the question. So,
Right now or in the future?
now.
No.
Yeah, now.
No.
Can you elaborate on that?
Well, just don't read the media about this, because there are lots of myths and lots of exaggerations, and as far as I know, there is no indication. Michael was very optimistic in his talk. He said 20 years. Is it true, Michael? Yeah. I think that I'm a little bit more realistic. Maybe Howard will disagree, but I say...
No, I'm a skeptic.
Oh, okay.
About
so we can't...
I mean, I think it's very hard, and that may not happen, but asking a concrete question, about current computing organizations, everyone in the audience probably won't know that very rudimentary computing devices which are very noisy, make a lot of mistakes, have been built and are pursued by people that want to test the possibilities and not let someone else do it while they're not looking. And those people are people like Google and IBM. So Google funds, John Martinez is the name of the physicist out of Santa Barbara, who developed much of the early technology for building quantum computers out of superconducting microwave circuits. And if you go to his website, the first thing you'll see is an enormous Google across the top. He's funded to really push the technological side and answer questions. IBM has elementary devices which you can run yourself online. So there's a simple programming language, and you submit a code, and it'll give you back answers. So these are certainly not people in the computing industry that realize the enormous potential and are pursuing it. I think they're people who realize that something might happen, and they better know about it, what's going on. They better be in the game.
I asked that question. Two pieces to the answer. IBM are touting 15-qubit online software as a service, free quantum computing.
Yeah, that's probably the thing I'm referring to, the number of qubits I didn't have.
They'll do 25 qubits.
Well, I can...
Gobsmacking. But sorry, to go back to the original question, talk to the security industry people, and they say, Moore's law, we've dealt with processing power increases before. I'd like you to comment, if you would, on the difference between Moore's law and what we're getting here.
Well, I don't know that I can say too much, other than Moore's law is perceived to have to inevitably have limits, because you can pack more stuff in only by making things, the elementary bits smaller. And eventually you get to the level where the elementary bit is an atom. And so there is, in principle, a limit to saying it can always get better. I don't think we can say as to how, scaling of improvement in attempts to do quantum computers with, I mean, you mentioned this number of qubits. in these IBM machines. I mean, the DWave, there's a company called DWave, and DWave has computers with thousands of qubits. But it's not a fully fledged machine like the IBM one. What their machine does is it solves optimization problems essentially by finding the lowest energy state of a system.
Well, but this is enough to solve all the practical problems we
Or does it solve the factoring problem?
Yeah, you can solve the factory problem. Well, for small instances, obviously.
Okay.
So this is the DWave series of computers which we have access to, and we are working with Michael and our group. By now they have 2,000 qubits. Yes, it's interesting in many respects. Number one is, as Howard said, this machine solves a single problem, but a single problem which has a generic power. So this means many other interesting problems, in particular NP-hard problems, can be in principle reformulated in the QUBO optimization problem DWave can solve. It's interesting to note that this idea of building a specialized machine for specific tasks has spread from quantum computing to classical computing. So there are now two companies in Fujitsu is one in Japan, building classical computers trying to simulate the quantum annealing which is used by DWave. So I see this kind of side effect, the influence from quantum computer towards classical computer, as one of the very positive aspects of quantum computing. And this is also related to another technique which we studied a long time ago here too, which I like to call dequantization. Dequantization is the study of an efficient quantum algorithm which inspires you to build a classical algorithm which is as good as a classical one. And the typical example, which is easy to understand, is the following. So you have a black box which computes a function from 0, 1 to 0, 1. And then the black box computes a function which you don't know. There are 4 possibilities. And you would like to experiment with the box to decide whether the function actually computed by the box is balanced or not. 2 functions are balanced, 2 functions are not, are constant. Now, classically, it seems that you need to access a black box twice to compute in 0 and in 1, and then compare and decide the solution. Quantum mechanically, you can do it one access of the black box. And for many years, it was claimed, but never proved, that you can't do classically with one access. And you can do it classically. And there are many, many examples. And recently, there was an 18-year-old student from the University of Texas, which dequantized one of the hopes of problem which was thought that would be easy to solve quantum mechanically but not classically. Going from the quantum mechanical solution, he obtained a very performing, very efficient classical solution. So I think that these 2 tendencies, complement and in my way show a positive side effect of the development of quantum computing.
So are those problems practical problems? So there's a question here, has a quantum computer solved any practical problems yet?
Well, what do you mean practical? You have to define.
I would certainly say no. I mean, by you mean practical, I mean, as Chris said, depends how you define practical. So, but my definition would include the notion of quantum advantage or something. You know, they're doing something better. Has this been demonstrated? And I think not yet.
Well, with DWave, you can solve many problems in graph theory, which are extremely practical. Michael can tell you.
Like the traveling salesman problem.
Well, independent set, your set, and many others. The issue here is the noise. So this means the probability of getting the correct solution, the scaling, how big instances of the problem you can solve, and the third issue here is how you test that the solution is correct or not. Because you mentioned factoring. If I have a quantum algorithm which factors, and I give you a number, you give me the factors, so it's easy to test whether the solution is correct or not. But if you have quantum algorithms trying to solve the maximum independent set into a graph, then testing correctness is as difficult as finding the solution.
Right, but it sounds like you're saying that you have to know what the answer is before you compute the answer.
Well, why should you want to compute if you know the answer?
Well, exactly. That seems to be, part of the weirdness of quantum computers. That
Well, I think even classical computations, if they get complicated enough, it's hard to check the answer. Is this not true?
Yeah.
I mean, all areas of science to some degree or another face this problem,
Right.
and certainly physics does. I mean, when is an experiment that's performed and published in Nature believable enough to be accepted as being valid? And so, okay,
Yep.
I mean, there are standard ways in which the likelihood of correctness is tested. These are not mathematical proofs, but other people reproduce the results independently. You approach the problem from a completely different direction and get the same answer. All these sorts of things. So that's pervasive, in science outside of quantum computers.
Yeah, well, that's, in a sense, this kind of opacity of quantum computing is very similar to the opacity of deep learning. So you have a combination there of a huge database with layers of approximations, and it's very difficult to see whether the solution is correct or not. And even if you are able to show that the solution is correct, it's very, very difficult to try to understand why it's so.
That's a very important point. I mean, if you're asking to factor a large number, and if you can do this factor, you get into this guy's military computer or whatever else, then that's fine. If you don't know how it was done, it really doesn't matter.
Yes.
You just get a concrete answer. But I can mention quantum simulation as an activity which is very common nowadays in physics labs, where you're trying to understand a complicated physics problem, a material problem. There's lots, oodles and oodles and oodles of atoms and molecules in there and all this stuff. What does it do? How does it behave? With classical computation, you can trace the steps, and you know what happened and why it happened.
To some extent.
Well, to some extent. If they get too many, I guess it can become
like
too much of a tangle.
Yeah. Deep learning, you can't really.
But in a quantum computer, it'll give you a result, and because the algorithm is in some sense intellectually impenetrable in a conventional classical sense, you don't quite know what the hell happened.
I actually asked the question about the practical solutions, and I think the answer before actually answered that, in that it's helping people to look at their algorithms and their classical approaches with a new way of looking at them from the quantum world and from the algorithms that have been developed through the quantum world. So I think it obviously is doing something practical, even
Yes, yeah. But
mean, that-
this is indirectly. It doesn't matter.
For the physicists, there is a big question, a big ask, which is an extrapolation of what Chris was saying there, and that is, can someone come up with an alternative way of formulating a theory of physics which gets all the answers right, like quantum mechanics does, but is not so weird and impenetrable? I mean, this is what Einstein was after.
Oh, yes.
And of course, I mean, no one has been able to do that, and I don't know that there are maybe a few people out there who still think it may be possible. But what you certainly can do is you can come up with penetrable models, classical, in other words, models, of certain phenomena in quantum mechanics. The thing that makes quantum mechanics weird is that it has to provide the correct answers to every question you want to ask. In a classical conception of a physical system, the nature of the system is modeled concretely. There's an assumed isomorphism between the algebra that's involved in setting up this set of equations that allows you to see how this thing moves in time, and reality. You know, there are elements of reality associated with every variable, and there's a variable associated with every element of reality. In quantum mechanics, the scenario is completely different. You don't have that one-to-one connection, and so you need asking different questions can lead to incompatibilities in the way the physical system should be modeled. I mean, the classic examples, or the words that go with these sorts of things, are wave versus particle. You know, electrons, when you send a beam of electrons through a couple of slits in a screen, you get an interference pattern on the other side. I mean, this is a fact. In fact, you can watch that experiment being done on a computer screen where the beam is so dilute that you send it through and you get one electron hits the screen there, and boom, you get a scintillation. And then there's another one that's over here, and there's another one that's over here, and gradually they come. And eventually, somehow, these things all know that we have to line ourselves up in bright and dark strips. It's an interference pattern. There's no way you're going to get that by saying that an electron is a little ball that goes through one of these slits or the other. And this feature, but there are other experiments you can do where the electron looks like a little ball. I mean, all these scintillations. Well, something hit it, and it hit it right there. And so it's this need to embed the answers to all potential questions, ways that you can look at the system, that makes quantum mechanics weird. It's not just that it makes quantum mechanics weird. It says the world is stranger than we had previously thought. We cannot capture in a straightforward way a clear conception of what is actually out there. We no longer have a concrete picture. This is something that Bohr said over and over again. We no longer have a concrete picture about what the bits and pieces are. If you take the picture of an atom as it's often popularly presented, that an atom has got this positive charge in the middle, there's a nucleus, and it's a bunch of electrons going around, it's a planetary planet, which Bohr did introduce that model. You can't describe, I mean, that model just falls apart. You cannot describe a real atom that way.
Chris?
Can I say a few things
from
the more mathematical part?
Yeah.
So there is a very fascinating book by Adam Becker called What is Real? Was the unfinished quest for the meaning of quantum physics, which appeared in New York last year. Yeah. And I agree with what you said, yeah. But I would like to point out that this is according to the current knowledge of and understanding of physics, that there is no compelling evidence that there is no better way to explain this. Third, that this battle of ideas between Einstein and Bohr, we started with the Solvay Institute discussion in 1927, which...
Well, yeah, it started before that, but yeah, that was a famous one, yeah.
Yeah, which, you know, in the general public understanding, finished with Bohr winning and Einstein lost. Apparently, according to this book and some other readings, is just the opposite. So Einstein won the battle, science and logical, but Bohr won it in propaganda.
I'm on the other side.
Yeah, and it is interesting. I will cite something which you know you wouldn't believe that will happen in science. You'll see that this comes from politics. So Robert Oppenheimer was quoted saying that one of the dividends from Copenhagen school, Bohm, Oppenheimer said, if we cannot disprove Bohm, then we must agree to ignore him.
This is Bohr or?
Oppenheimer.
No, but
He said that of Bohr.
he said that of Bohr.
To Bohm. Bohm was the Bohemian.
Yeah,
he was a dissident, and apparently they couldn't disprove with arguments, scientific arguments, his. And they say if we can't disprove him, then we must ignore.
Let me change the emphasis in this business about what you can prove and disprove and things like that, because this is not the point in physics. I don't know of any major physics that was done by proving a theorem. What's the point is what ideas are fruitful. What ideas simply produce progeny over and over and over again. This is also an essential point about how do you win the Nobel Prize. What you do has to be fruitful. It has to trigger things in other people's brains that they can build on. And the thing about quantum mechanics is that it has been unbelievably fruitful. It is unbelievably fruitful. It's not a question of absolutely proving that this is so or that is so, and that proving that there must be some other way of doing it. People have tried, and the fact that they failed is not a proof that some other trial cannot be successful. People have tried to concoct something else. And quantum mechanics is stunningly simple at its mathematical level. And it's stunningly unintelligible at an ontological and philosophical level. But the proof of the pudding as to it's the thing to keep pushing is that it's managed to get everything right. And when you wonder, I mean, take the Manhattan Project. I mean, my God, here you have this nuclear explosion. It's not like sort of the automobile, which was developed by an elementary idea and people building on and improving and improving. It was simply the theoretical conception and understanding of what this goddamn atom and this nucleus was and how it should behave. You designed something and it went boom the very first time. That is rather spectacular.
And a bit unfortunate.
It's also a bit unfortunate. So I've had that anecdote in my brain for many years and I've never used it but this is a very understanding audience, so I thought I could use it.
Okay, so the top question up there is about scalability. No. So what would be the main obstacles for quantum computing to scale?
Well,
are they physical or mathematical?
Well, I think they're certainly physical. I mean, when people talk about scalability of building a computer, they're the physical obstacles. Some of those obstacles are surely simply engineering obstacles. That if you want to make something big and allow, well, I'll give you an example of a quantum computer computing platform which cannot scale beyond a certain point, and it's quantum computing with trapped ions. So an ion is an atom which has got one electron missing, and so it's got a positive charge. You can hold one such ion in an electromagnetic trap, and it's sitting there. You've got a single atom you can do experiments with. You can put 100 of them beside each other or put them in an array, and you've got a register. You've got lots of qubits. So this is one of the first platforms that quantum computing was developed for, or developed on, and the first practitioner, Dave Wineland, in this field, won the Nobel Prize, not for his quantum computing, but for developing these traps and doing sexy things with them. Now, the way that these computers, so they have a string of ions. Let's say there's 50 of these guys. 1, 2, 50. These ions interact, they're charged particles, and so they interact via the electrostatic force, the Coulomb force. And that means that if I kick it, it shakes. And there's 50 of these things, so there are lots of what we call normal modes, ways of shaking. The natural modes that this thing will shake. And those natural modes all have a frequency, have a separate frequency. And the way that they communicate between the qubits in these devices is that they transfer energy from the internal state of one of the qubits to the shaking. They create what we call a phonon. Mm-hmm. And then that shaking is seen by the guy downstream, and you can engineer it in such a way that this guy talks to that guy. Now you face the problem, because as you put more and more of these qubits, these ions into that string, the spacing of the frequencies between these normal modes gets smaller and smaller. And eventually you can't resolve them. I mean, the way that you excite the system is you take a laser and you give it a particular frequency and it hits that particular normal mode. You then have to hit another one. You do sequences of these laser pulses, and this is the way that you manipulate this thing. But if you just pack more of these things in there, beyond about 50, it becomes impossible to resolve it. So that strategy has a scalability problem. I mean, it has a scalability death.
Yep. And
different platforms will have different issues as to what makes it hard when you try and make it bigger. One approach which is being followed by another group of iron people to overcome this sort of scalability problem is to do the communication between qubits more the way that you do in a regular computer. In a regular computer, we have all sorts of data out here. We have memory and stuff. We have processors, and we bring stuff in through pipelines, and we do stuff and we send it out. So their idea is to move these qubits around, bring them together so they talk to each other, and put them back. That creates its own engineering problems. You have to be able to slide these things around. It's not easy.
Yeah.
So each one of these platforms will have its own issues those engineering issues. And the other issue is that quantum systems become more and more fragile the bigger you make them.
Right.
So what's called decoherence. I mean, it's not like quantum systems are that weird that they're very odd, are rare. I mean, all atoms are quantum systems. They do their quantum thing, and they somehow their quantum aspect is protected. But when you string many pieces together and make a quantum system that has all these separate components, there's a tendency for the individual components to reveal their identity to the outside world by accident. And that the more of the things you got, the more problem that is.
Yeah.
So these I think are the two issues: engineering ones, which which are platform dependent, and just the fact that I mean, with a quantum computer, you're asking to have your cake and eat it, because the way to protect the quantum aspect of a very large system is to deny it any access to the outside world, to completely isolate it. But a completely isolated computational device is not very useful. You can't set it up, you can't put something in, you can't read something out, you can't manipulate it. So you want to preserve that integrity, which is usually hidden deep inside the atoms and molecules of a structure. You want to preserve that up at a more macroscopic level, where you can still actually point to things and prod them and manipulate them and not screw things up at the same time. You're trying to have your cake and eat it. It may be impossible.
You cannot communicate with a quantum computer except
through
a classical computer. So,
yeah, something has to talk to it from the outside.
Yeah, I've read recently a Russian-French physicist, Diakonov, has calculated that a useful quantum computer, which is thought to be having about 10,000 to 100,000 qubits.
Logical or physical?
Physical.
Physical qubits.
Physical.
Because logical is you need many physical
Yeah.
qubits to make a logical.
Yes, so Diakonov said that for 10,000, you need to process a set of continuous parameters that is larger than the number of subatomic particles in the observable universe, which for him this is a kind of indication that this quickly goes beyond the not only the engineering capability.
Yeah, I don't know. Yeah, I don't know what this guy specifically said. I mean, it's certainly true. Even going back to my simple example of 100 qubits, when I said there's 2 to the 100 potential arrangements, in that in some sense they all live at the same time in a quantum state, or you can in principle make a quantum state in which they all live at the same time. Yeah. There's no way that you're ever going to be able to manipulate all the 2 to the 100 complex numbers.
Yeah.
You can, but
the art
but
is
you may not need to do a computation.
Exactly.
You only have to live in part of the space.
Yeah, you need to live in sort of this, virtual reality for as long as is possible with the quantum algorithm, and defer the measurement till the very end step.
Yeah, you infer the measurement of the invariance, and you have to build the algorithm so that the manipulations, if it involves quantum gates sequentially, that the manipulations are manageably large or small.
So this gives me an analogy with AI. AI, started with big dreams, then it was a long winter, and now it's coming back more mature and with better results. But in quantum computing, the quantum algorithms, all the important ones, have been discovered in the early 90s. So this is Shor's algorithm, Grover's algorithm. Grover's algorithm is probably the only important algorithm which has been proved to be better, albeit with the polynomial speed-ups, than anything classical. But meantime, from early 90s to nowadays, there is no new idea, no new algorithm.
No,
and it's interesting that Shor himself, about 10 years ago, has written an interesting article trying to explain why there is this, lack of new algorithms. Yeah, so one of the reasons in that article was that the weird nature of quantum mechanics doesn't match well with the algorithmic thinking of people developing algorithms. So maybe that's one of.
You mean that we're too dumb to figure them out?
Okay,
I mean, this is certainly a big. This raises my skepticism level too. The dearth of algorithms. They're not just coming out of the woodwork.
So we are running out of time. So I'd like each of you to give your view on the future of quantum computing. 20 years.
Oh. Each of the members of the audience?
No, each of you two. I'm sure everyone would love to. But.
When you ask questions about the future of quantum computing, for me, the question becomes as much sociological as scientific.
Yep.
It's not going to go away in the short term. I'll give you 2 examples. Last year, Trump signed a piece of legislation called the National Quantum Initiative Bill. And that is the US's commitment to pursue quantum technologies broadly, and ultimately means money. Also, I think last year there was an £80 million infusion into the UK's quantum technologies program. So governments are still invested in the hope that this so-called second quantum revolution doesn't just necessarily, maybe doesn't produce a quantum computer, but spits out sort of marketable, useful technology, devices, and there's money being pumped in, and so as long as that's there, the effort is going to go on.
So are they pumping the money in because they expect something out of it? Or,
Fear.
Yeah.
Well,
Or is it
fear
just
is one aspect. If there's a game which other governments are playing, and a third government needs mentioning is China, I can't put my finger on a particular program. I know some people, but China definitely has a focus on various sorts of quantum technologies. I mean, you know, when something came out on the web last year about a quantum radar, everyone was just going up and down, you know, all the military people around the world. There are definitely things that you can do better quantum mechanically, which are not directly related to computation. And this is this quantum metrology, that all measurements are contaminated by imprecision and noise. And quantum mechanics says that there's a ultimate limit to, you have to have some noise, it says. You can't make any measurements perfect. This is Heisenberg's uncertainty principle. But what you can do is you do your measurement in such a way that you minimize the amount of noise affecting your particular measurement. You put the noise somewhere else, and you make your measurement more precise. And one example where these ideas are followed through is in designing the latest generation of clocks. Now, you must think that coming up with a clock is not a big deal. Coming up with a clock is an enormous big deal because the GPS works entirely off clocks. You have a highly precise clock, so you can time pulses going backwards and forwards with the satellites. And there's no question that the original atomic clock has been supplanted by a new generation, and using quantum techniques to reduce the imprecision in the measurements you make that are used to stabilize this thing, that you can in principle do better. And so these sorts of targets are being pursued by government. So it's broader than just this notion we're going to have this thing can crack codes.
Yep.
It's broader than that. It's that quantum mechanics, with its unusual aspects, is fundamental to engineering on the micro scale, and we better understand it, and we want to understand it, and who knows what's going to come out, but something's going to come out. That's more or less the way science works.
Chris?
I agree. Quantum information theory is interesting. It will produce interesting results. I still hope for a no-go theorem, but I have no predictions regarding the pace and usefulness of quantum computers, and much less about how much money you can make of them. And probably because at the end, if you give me 1 minute, I would like to pay tribute to Bob Doran. Michael started the first lecture dedicating to Bob his lecture, and I would like to say a few words about Bob. Bob was the starter, the head of department who has started the process of building a research-oriented multinational department. He founded the Computer Science Museum, and he founded and organized the first 9 editions of this series of lectures. So, and personally, I owe immensely to Bob, so he is dearly missed. Thank you.
Thank you, Chris. Okay, so I think we've got to close it off there.
I didn't drink.
You didn't drink, that's good. There are some really important questions that we haven't managed to cover, like what's next week's lotto numbers and who is Grant Robertson? So, so it's a shame we haven't got to all of them, but I think it has been a fascinating debate, panel, whatever you'd like to call it. So thank you very much.
Thank you for coming.